Okay, in this lecture, we're going to discuss the method of reduction of order, which is a useful method for constructing a fundamental set of solutions for some second-order linear homogeneous differential equation if we know or have found one of its solutions. So let's consider the following. Suppose that we know or we have found one non-zero solution, let's call it y1 of t, of the second order linear homogeneous differential equation shown here. And we want to find the general solution. So we know from our previous section that in order to find the general solution of a second order linear equation, we need two solutions that form a fundamental set, that is, they have non-zero Wronskian. So the question is, well, how do we find a second solution? And here is our method. To find a second solution, let us consider a function of the form y equals v of t times y1 of t, where v of t is some function that we're going to try to find, and we're multiplying it by y1, our first solution. So in order to find v that would make this function a solution to our differential equation, we need to substitute this function into our equation and see when it would be satisfied, which means that we need to find our first two derivatives. So here, by making use of the product rule to differentiate, our derivative, y prime, would be given by the derivative of v prime, times y1, plus v times the derivative of y1 prime. And then our second derivative, y double prime, using the product rule for each of these terms, we would have the second derivative of v double prime, times y1, plus v prime times y1 prime. And then we are adding, when we move to the second term from our first derivative, we again apply the product rule, and we would have v prime times y1 prime plus v times y1 double prime. Or if we collect these two middle terms, we notice that they're the exact same expression, v prime times y1 prime. We get v double prime times y1 plus 2v prime y1 prime plus v prime times y1, plus v times y1 double prime. And now let's take these expressions and substitute into our differential equation from above, equation 1. And let's see what we have. So the first term was y double prime, which we just found as v double prime y1 plus 2v prime y1 prime plus v times y1 double prime. And then we are adding p of t times our first derivative, which was v prime y1 plus v times y1 prime. And then we add q of t times y, where y was defined as v times y1. And in order to solve the differential equation, which is homogeneous, we need this to equal 0. So now if we expand everything and collect like terms based on the order of the derivative of v, let's see what we have. So collecting like terms based on the order of my v derivative, let me start by collecting everything that involves v double prime. And the only expression I have with the v double prime is this first one. So we have our v double prime times y1. And then we add to that, well, let's group everything that involves the first derivative of v. So looking at my expressions with the first derivative of v, we just have these two terms. So if I group those together and factor out v prime, I'm left with 2y1 prime plus p of t times y1, all times the first derivative of v prime. And then I add to that, if I group all of the terms that involve just v, I have these three terms. So grouping them and factoring out v, I am left with y1 double prime plus p of t times y1 prime plus q of t y1 all times v, and I still need this to equal 0. So now if we look at this last term, if we look at the coefficient in front of v, we have y1 double prime plus p of t y1 prime plus q of t y1, which is exactly my differential equation from above with y1 substituted into it. And we know that y1 was a solution of that equation. So when I plug in y1 to that expression, it gives me 0 because it was a homogeneous equation. So this last term becomes 0, and we are left with y1 v double prime plus 2y1 prime plus p of t y1 times v prime is equal to 0. So what we get by substituting into our equation is the differential equation shown here, the one we just found in simplified form. And notice that this is a first order differential equation in terms of the function v prime. So since that v term disappeared, all that we're left with is something involving v double prime and v prime, which we can consider a first order equation of the first derivative, v prime. To make that a little clearer, we could make a change of variables here. If we let w of t be the derivative of v, let's call it v prime, then our first derivative, w prime, would be the second derivative of v. And I could rewrite the differential equation I just found as y1 times v double prime, which is just the first derivative of w, plus 2y1 prime plus p of t y1 times v prime, which is w, equals 0. And we see this is now a first order differential equation in terms of w. It's first order linear and first order separable. So I could solve that equation as a first order linear equation, say using integrating factors, or as a separable equation. And once I know what w is, which is v prime, so once I have found v prime, we can find v by integrating. And once we know what v is, then we have found our second solution from v. Our second solution would be whatever v function we found times our first solution, y1. So this method is called reduction of order because we reduced a second-order linear homogeneous equation into a first-order equation, which we know how to solve. Hence, reduction of order. So now that we've discussed this technique in general, let's look at an example making use of this. In this example, we are asked to verify that the function y1, which is equal to t, is a solution of the given second-order linear homogeneous equation, and then use the method of reduction of order to find a fundamental set of solutions. So let's start with the first part of this problem, verifying that the given function is a solution. So here, if we have the function y1 of t is equal to t, then our first derivative, y1 prime, would be 1, and our second derivative, y1 double prime, would be 0. So if we substitute these expressions into our differential equation, we have t squared times y double prime, which is 0, plus 2t times y prime, which was 1, minus 2 times y, which was t, and this leaves us 2t minus 2t, which is indeed equal to 0. So when we substitute into our differential equation, it is satisfied. So we can say here that the function y1, which is just equal to t, is a solution. Now for the rest of this problem, to find a second solution and find a fundamental set of solutions, I'm told to use the method of reduction of order. And that method says, well, to find a second solution, let me maybe call it y2 of t, we take some function v of t, and I multiply by my first solution, y1. So in this case, we have v of t times y1, which was just t, and then we want to find v of t, which would make this a solution of our equation. So let's find our first two derivatives, starting with y2 prime. So by the product rule, y2 prime would be v prime times t plus v times the derivative of t, which is just 1. And then for our second derivative, y2 double prime, using the product rule for our first term, we would have v double prime times t plus v prime times the derivative of t, which is 1, and then plus differentiating our v factor on the end, we get another v prime, which leaves us with v double prime times t plus 2v prime. So let's take these expressions and substitute into the ordinary differential equation that we were given. So our equation was t squared times the second derivative of y, which we just found as v double prime t plus 2v prime, then plus 2t times our first derivative, which was v prime t plus v, and then minus 2 times y, which was just v times t. And we need this to equal 0 to give us a solution. So let's expand and group some like terms. If I distribute my t squared out in front, I have v double prime times t cubed plus 2t squared v prime plus, if I distribute my 2t, I get 2t squared times v prime plus 2tv. And then on the end, I have a minus 2 times vt, or 2 times tv, is equal to 0. And as we expect, as we saw in the general case, all of the terms involving v disappear. Our 2tv minus 2tv disappear. And then if we collect all of the terms involving v double prime and v prime, we are left with t cubed times v double prime plus 4t squared times v prime is equal to 0. And this is now a first-order differential equation of the function v prime. So to solve this, well, we could maybe first make a change of variable. Let's introduce a new function w, which we will define as the derivative of v, so that my derivative of w prime, is equal to the second derivative of v. So if we rewrite our equation that we just found in terms of w, we have t cubed times v double prime, or the first derivative of w. Let me write it in Leibniz notation, dw dt, or w prime, doesn't really matter, plus 4t squared times v prime, which is what we were calling w, is equal to 0. So what I'm left with here is now a first order linear equation, which is homogeneous in terms of w. And I know how to solve this type of equation. It's first order and linear, so I could either use integrating factors, or it's also separable. I could use separation of variables. And usually separation of variables is a little bit easier, so let's make use of that approach. So let me say here, using separation of variables, we would rewrite our equation as t cubed times the derivative, dw dt, equals negative 4t squared times w. And so separating the variables, we have dw over w is equal to negative 4t squared divided by t cubed, which leaves me negative 4 over t dt. And so integrating on both sides, we have the natural log of w is equal to negative 4 times the natural log of t plus some constant. Let me call it c1. Now, using properties of natural logs, the right-hand side I can rewrite as the natural log of t to the negative 4th plus c1. And so by exponentiating on both sides, I find w, which is a function of t, would be c1 times t to the negative fourth power. So I know what w is, but recall w was the derivative of v prime. And I want to find v. So if I know the derivative of v, to get v itself, I would just integrate on both sides with respect to t. And I find that v of t, my antiderivative, would be c1 divided by negative 3 t to the negative third power plus some other constant c2. So here we have an expression, in general expression, for v of t, which involves these arbitrary constants c1 and c2. And c1 and c2 could be any constants that we want here. So we usually choose easy constants or simple constants that would make this v of t expression clean up nicely. So for this particular problem, I might look at v of t where c1 is negative 3, so that I get rid of my fraction out in front of t to the negative third, and c2 is 0. So if I consider the constants c1 equals negative 3 and c2 equals 0, I find that v of t would be t to the negative third. And therefore, my second solution, y2 of t, which was defined as v of t times y1, gives me t to the negative third power, which I just found for v of t, times y1, which was just t, and that leaves me t to the negative 2. So we have found a second solution of our given equation, t to the negative 2, and to show that we have a fundamental set of solutions, we need to calculate the Wronskian of y1 and y2. So for the last part of this problem, if we look at the Wronskian of y1 and y2, which are functions of t, we would have the determinant of the 2 by 2 matrix, where our first row would be y1, which was t, and y2, which we just found to be t to the negative 2. And our second row would be the derivatives, 1 and negative 2t to the negative third, which gives us negative 2t to the negative 2 minus t to the negative 2, or negative 3t to the negative second, which is certainly non-zero. So we have found that our two solutions, y1, which was t, and y2, which was t to the negative 2, form a fundamental set of solutions of our given differential equation, which means that the general solution is then just a linear combination of y1 and y2.